briefly told you about units and dimensions, fundamental quantities and derived quantities, let me demonstrate to you an extremely important, vital and critical application of dimensional analysis. You know, using dimensional analysis, we can connect physical quantities. If we know about a certain physical quantity and its dependence on other physical quantities, if we know about a physical quantity and its dependence on other physical quantities, and if we know that this dependence is of a product kind, and if we know that this dependence is of a product kind, dependence of one physical quantities on a certain number of physical quantities, that will occur in products of powers or powers of products of other physical quantities, we will be able to arrive at certain results and relationships, which is what the agenda of this session is. Now, let's talk of a simple pendulum. A simple pendulum has a certain length L with a mass m attached at the end, with a mass m attached at its end, and the time period of the pendulum, the time it takes for a full oscillation. It starts from this point, it goes here, it goes to this extreme, comes back to this point, it starts from A, goes to B, goes to C, comes back to B, and come back to A. That's a full time period. It will depend on three essential things: the mass of the bob attached at the end, L, which is referred to as the effective length of the pendulum, and the value of G, which is acceleration due to gravity. These are the three things on which the time period will depend, and the dependence is of a product kind. Which means to say that, hey, the time period would be like, the formula for the time period would be like some constant K, and then there is mass m to the power x, length L to the power y, and then there is G, acceleration G to the power z, kind of a dependence is what it has. K is a constant, of course, which can be obtained only experimentally. But if this is the kind of dependence, then x, y, z can be obtained from dimensional considerations. How does one do that? Dimensional considerations means now the K is, of course, a constant which is dimensionless. So dimensions of T, which is this, the time period, is the same as dimensions of m to the power x, and L, which is dimensions of length, to the power y, and G, which is meters per second squared, or LT to the power -2 whole to the power z, right? Now what we need to do is we need to equate powers of m, l, and t on both sides. We need to equate powers of m, l, and t on both sides and solve for x, y, z, and then we have, if once we solve for x, y, z, we'll have a formula for the time period of a pendulum with the help of dimensional analysis. Now, what's the power of m on the left hand side? 0. What's the power of m on the right hand side? X. So very clearly x has to be 0. What's the power of L on the left hand side? 0. But what's the power of L on the right hand side? Y plus z. Y coming from here and z coming from here. So y plus z, right? What's the power of T on the left hand side? 1. And what's the power of T on the right hand side? -2z, right? So we have very clearly z equal to -half. And if z is -half, y is -z, so y will be half. So we very clearly have a formula here. X is 0, y is turning out to be half, y is turning out to be half, x is turning out to be 0, and z is turning out to be -half. And then that leads us to a result. Time period of a simple pendulum is k, m to power x, which is 1, L to power y. L to power y means L to power half divided, and g power z means g power minus half, g power minus half, right? Which is very clearly t equal to k root L by G. And from experiment, k can be found to be 2 pi, and therefore dimensional analysis comes a long way in helping us come closer to a result. You know, this k cannot be obtained using dimensional analysis. This has to be obtained using using experiment or some other indirect means, but the rest of the stuff, x, y, z, which are part and parcel of a product formula, can be obtained with simple dimensional considerations. In exactly a very similar manner, what we'll obtain is, we have a sphere of mass m and radius r. Sphere of mass m and radius r. And it's very slowly moving down a viscous fluid with a velocity v, speed v. And the property, the viscosity of the fluid is eta. This is the viscosity of the fluid. Viscosity of the fluid, right? Now, when this mass moves with a velocity v through a fluid of viscosity eta, then the fluid exerts on it a viscous force F. F is the viscous force exerted by this fluid on this mass, which is a resistance, which is force of resistance or a viscous force. Viscous force, right? That is because of the viscosity of the fluid, right? And we know that this viscous force will depend on three things. One, the viscosity of the fluid. Two, the radius of the sphere. Radius of the sphere. V, the velocity. V, the velocity. In fact, the result can be written as the viscosity of the viscous force that the sphere will experience, the viscous force that the sphere will experience would be k times some eta to the power x. Eta is the viscosity. Radius to power y, r is the radius to power y. V is the speed with which it is plunging down, which is resulting in the viscous force opposing the velocity v. Now, so dimensions of F would be dimensions of eta whole to power x, dimensions of r whole to power y into dimensions of v whole to power z. And what is dimensions of F? Dimensions of F would be mLT to power minus 2, right? Kilogram meters per second squared. Kilogram meters per second squared. Mass, length, time to power minus 2. The dimensions of viscosity is m, L to power minus 1, T to power minus 1. These are the dimensions of viscosity, a property of the fluid. Whole to power x into radius r. R is length. So length to power y into v, which is length by time, L by t to power z. Now one could solve for x, y, z. Okay. First of all, equate powers of m on both sides. Equate powers of m on both sides. We have 1 on the left hand side as the power of m, and on the right hand side, as you can see, what's the power of m? X. X, right? So x must be 1. X must be 1, right? Let's equate powers of L on both sides. The power of L on the left hand side is 1. The power of L on the right hand side is like minus x plus y, right? Yes or no? Minus x plus y, and then there is a plus z, right? Plus z. See? 1 equal to minus x plus y plus z. And x is already given to be 1. X is already given to be 1. So if you plug in x equal to 1 here, you get y plus z equal to 2. Right? That's obtained by equating powers of L, dimension L on both sides. Time, minus 2 on the left hand side. Minus 2 on the left hand side means minus x coming from here, and then minus z coming from here. Minus z coming from here, right? And very clearly, put x equal to 1. Put x equal to 1. So if you plug in x equal to 1, you get minus z equal to minus 1 or z equal to 1. Z equal to 1 is what you get if you plug in X equal to 1. And if Z is 1, you plug in Z equal to 1, you get Y equal to 1. You get Y equal to 1. Good for us. Simple looking formula for the viscous force. X is 1, Y is 1, Z is 1. So the viscous force experienced, as you can see, the viscous force experienced is going to be K times eta to the power 1, R to the power 1, and V to the power 1. That's the viscous force. That's the viscous force. And out of experiment, it is found that this K out of experiment is found to be 6 pi. Is found to be 6 pi. So the viscous force turns out to be Kf equal to 2 pi eta 6 pi eta Rv. Yes or no? So the viscous force F turns out to be 6 pi eta Rv. And this viscous force, this result is commonly referred to as Stokes' law. Is commonly referred to as Stokes' law, and so on and so forth. So a large number of physical quantities can be connected, interconnected, intertwined, put on the same fabric, and important relevant results could be obtained with the help of sheer dimensional analysis. Of course, the limitation is that these constants that feature here, for example, in the time period, this constant K, now this is not within the purview and jurisdiction of dimensional analysis. This has to be obtained mostly by experiment or some other means. This constant K here in the formula for viscous drag or viscous force or resistance, this cannot be obtained using dimensional analysis. That's a limitation. It's not like you can forget all about everything and just deploy dimensional analysis to obtain the world of physics around you. No. You can obtain some things. You can't obtain all things, but then you can obtain some important things. You can come to the point of relevance, and you can take life from that point onwards. So then, and of course, the other limitation is it can only derive formulas in which dependence of one quantity takes place on other quantities in the form of product of powers. But if it is not product of powers, the dimensional analysis doesn't work that effectively. Thank you so much, but we have more to learn, more to do very shortly in a few more sessions. Thank you. Bye-bye.